Chapter 1. The hydrofluoric acid bathtub scene. More than just a smell. There's a moment early in Breaking Bad that imprints itself into the minds of viewers forever. A moment of shock, disgust, dread, and fascination. Jesse Pinkman, trembling and clueless, stands over a bathtub with a body and a jug of hydrofluoric acid. Walter White, calm but irritated, tells him precisely what to do. It has to be plastic. Jesse doesn't listen, and moments later, the ceiling collapses as the bathtub and its horrifying contents come crashing through the second floor. It is one of the most iconic scenes in television history. It is also one of the most misunderstood, most exaggerated, and most mythologized pieces of TV chemistry ever filmed. But here's the real question, the one that scientists, chemistry teachers, and curious fans have debated for years. Would hydrofluoric acid actually melt a bathtub? Would it really liquefy a human body? Would it eat through floors and leave a catastrophic goo-filled hole in your house? To answer these questions, we need to do something few ever do. We need to slow down and examine what hydrofluoric acid actually is, what it does, and what it definitely does not do, no matter what Hollywood wants you to believe. And so, in this first chapter of our deep exploration into the real science behind Breaking Bad, we're going to peel back the layers of drama and look instead at truth, often stranger, more frightening, and more fascinating than the fiction. Because hydrofluoric acid isn't a magical body-melting superacid. It's something far more unsettling, not in the theatrical, ethereal house way the show depicts, but in a way that is invisible, deceptive, and clinically terrifying. To understand the truth behind the bathtub scene, we need to begin with a brutal, unsettling reality. Hydrofluoric acid is not powerful because it melts things. Hydrofluoric acid is powerful because it doesn't. This is the first great misconception. Most people hear the word acid and immediately imagine sizzling surfaces, dissolving metal, and bubbling destruction. We picture Hollywood vats of green ooze melting steel beams. We imagine cartoonish drips that burn straight through floors. But hydrofluoric acid doesn't behave like that. It doesn't smoke. It doesn't bubble. It doesn't hiss or foam. It doesn't look like it's doing anything. It doesn't even look dangerous. Hydrofluoric acid is almost always clear. It is almost always silent. And worst of all, it is almost always slow. The horror of HF lies in its patience. It is a chemical that doesn't dissolve objects instantly. It destabilizes them over time. It creeps. It seeps. It infiltrates. It penetrates deeply into materials, especially organic tissue, long before the victim even realizes something is wrong. And that brings us to the most disturbing truth of all. When HF touches your skin, it doesn't burn immediately. It slips under it, quietly. There may be no pain for minutes, sometimes hours, sometimes a full day. The victim may think nothing has happened until the calcium inside their body begins to bind with the fluorine ions in the acid, causing internal chemical destruction that no Hollywood effect could ever truly capture. If this sounds gruesome, that's because it is. But it is also the key to why Breaking Bad's depiction is scientifically flawed. Hydrofluoric isn't the violent, explosive, melt-through-your-house liquid portrayed in the show. It's worse, but in a very different way. Deep tissue penetration. The true terror. When HF contacts skin, it doesn't char it or bubble it like sulfuric acid might. Instead, the HF molecule moves inward, passing straight through the outer layers, slipping beneath nerves, and moving toward deeper tissues. This is why victims often feel nothing at first. The destruction happens inside the body. It binds aggressively to calcium and magnesium, stripping those minerals from cells, bones, and the bloodstream. This can cause cardiac arrest, bone decalcification, muscle failure, systemic toxicity, internal chemical burns far from the original contact site. Professionals who work with HF wear specialized equipment not because the acid will melt through their gloves instantly, but because one drop can kill quietly, This contrast between Hollywood's burning goo and reality's silent infiltrator is fundamental to understanding why Breaking Bad's bathtub disaster is scientifically exaggerated. Hydrofluoric doesn't instantly liquefy a human body. Hydrofluoric doesn't instantly melt a bathtub. Hydrofluoric doesn't instantly eat through floors. It does pose one of the deadliest occupational hazards in chemistry, but not in the way TV portrays. Porcelain versus HF, the show's first big leap. This brings us to the next major question. Could HF actually dissolve a bathtub? In most cases, the answer is no, not even close. A modern bathtub is usually made of porcelain enamel, ceramic, fiberglass, acrylic, or a cast iron body coated in enamel. HF can etch some ceramics. It can weaken porcelain after extended contact. It can cause slow surface level damage, but melt, collapse, eat straight down into the floor below. No, that level of destruction simply isn't in HF's nature. And here's the irony. HF is dangerous because it is not aggressive enough to make its damage visible. Walter White, being an actual chemist, knew this. Jesse, being Jesse, did not. But even Walter White's warning, it has to be plastic, exaggerates reality. Yes, HF reacts aggressively with glass. Yes, it must be stored in plastic containers. Yes, a ceramic bathtub is the wrong choice, but an HF-filled bathtub would not collapse through the floor in a matter of hours. It would more likely become discolored, weakened, etched, and dangerous, but not catastrophically obliterated. I'll get the dramatic cinematic disaster scene in the show. You'd need a much different set of chemicals and a much longer timeline. Hydrofluoric acid is deadly, but not Hollywood deadly. If there's one question viewers have obsessed over since the episode aired, it's this. Could hydrofluoric acid actually dissolve a human body? The short answer is, not the way Breaking Bad shows it. Not even close. But the long answer, the true scientific, deeply unsettling answer, is far more complex, more fascinating, and more disturbing than anything the show depicts. To understand what hydrofluoric acid can do, we first have to understand the composition of a human body itself. A human body isn't one thing. It's many things. A human body is not a uniform substance waiting to melt like wax. It is a mosaic of structures, skin, fat, muscle, tendons, cartilage, bone, connective tissue, organs with different chemical compositions. Each of these materials responds differently to acids, some more reactive, some less. For example, skin contains proteins and fats that acids can attack, but slowly. Muscle is dense and water-rich, meaning acids must diffuse inward. Fat is hydrophobic, meaning water-based acids have trouble interacting with it. Bone is mineralized and requires powerful acid to dissolve, often over days or weeks. A single chemical, even a dangerous acid, cannot uniformly dissolve all components of a body quickly. This is why real-world body disposal stories from forensic science, not entertainment, almost always involve high heat, strong bases like lye, or strong mineral acids like sulfuric or nitric acid, never hydrofluoric acid alone. This is also why Breaking Bad's depiction is more cinematic than chemical. To melt a body to the consistency we see in the show would require a far stronger acid, a far larger volume, a much longer time, far more heat and agitation. HF simply does not have the dissolving power to liquefy bone rapidly, nor does it aggressively break down fat. It focuses primarily on calcium-containing structures, and even that process is relatively slow. So when the show depicts a body turning into a pink soup, when the bathtub collapses under a wave of liquefied flesh, when the ceiling gives way, those visuals are driven not by chemistry but by storytelling. Why HF isn't a body-dissolving superacid? Let's look at some reality. HF is weak as an acid, chemically speaking. Despite its terrifying reputation, hydrofluoric acid is technically a weak acid in terms of dissociation. That means It does not release hydrogen ions as aggressively as strong acids. It does not behave like sulfuric or hydrochloric acid. It does not rapidly break down organic matter. The damage HF causes in living tissue is due to toxicity, not rapid dissolution. Most of HF's danger is internal, not external. HF kills by interfering with calcium in your cells and bloodstream. It causes systemic failure long before it dissolves anything visibly. Bone dissolution is slow. Because HF binds tightly to calcium, it can slowly demineralize bone, but not in hours, not even in a day. We're talking long durations, not Hollywood timelines. Flesh dissolution is extremely slow. Acids dissolve flesh by breaking peptide bonds, a slow process even under ideal conditions. If acids really liquefied humans quickly, crime labs would have no need for forensic anthropology. Real experiments. What actually happens? When actual researchers, chemists, forensic scientists, and science educators tested HF on various materials they found, clothing, weak damage, porcelain, etched, dulled, weakened, but not dissolved. Animal tissue, slow breakdown over hours or days. Bone, minimal effect without no catastrophic collapse. No instant goo, no bathtub eating event. In reality, the HF bathtub scenario would more likely produce a horribly dangerous toxic room, a discolored tub, a partially decomposed body, mostly intact, long-term surface damage, and no structural collapse. HF is a killer, but not a dissolver. But what about the ceiling collapse in the episode? That dramatic moment when the tub crashes through the floor is one of the most iconic in the series. But would it happen? Not with HF. Not with a modern bathtub. Not within hours. To collapse a floor, you'd need immense weight added suddenly, massive liquid displacement, structural beams weakened over a long time. HF provides none of that. Even if the tub cracked, the floor has joists, beams, flooring layers, structural redundancy. One weakened tub cannot catastrophically destroy the entire system. The show exaggerates HF to create a memorable scene, and it worked spectacularly. But scientifically, not plausible. Not close. Let's return to that iconic line from Walter White. The line that launched a decade of memes, reaction videos, chemistry explainers, and countless what-if debates. It has to be plastic. Fans quote it. Chemists nod at it. Non-scientists assume it means HF melts everything except plastic. But here's the deeper truth. Hydrofluoric acid doesn't melt plastic because of one thing: molecular reluctance. While HF is incredibly dangerous to biological systems and extremely aggressive toward glass and silica-based materials, it is surprisingly well behaved around many plastics. This is not because plastics are stronger. It's because plastics are chemically boring to HF. HF goes after silicon, silicates, glass, calcium-containing structures like bones, certain metals. But plastics don't give HF what it wants. No calcium, no silica, no reactive sites it can exploit. To HF, plastics are like a bland, flavorless snack food. There's nothing exciting to bite into. And that's why Walt tells Jesse to use a polyethylene container. Polyethylene and PTFE, like Teflon, are famously resistant to HF. But the bathtub Jesse chose? That's a different story. Porcelain, ceramic, enamel, HF's true enemies. Most bathtubs, especially older ones like the one in Jesse's house, are cast iron coated with porcelain enamel, a glass-like layer primarily made of silica. Silica, COS, is hydrofluoric acid's favorite food. HF loves silica. It reacts with it aggressively, producing hexafluorosilicic acid and silicon tetrafluoride gas. This means that HF can damage enamel surfaces, etching them, dulling them, weakening them. But, and this is the key point, Asterisk asterisk etching is not dissolving. Weakening is not liquefying. Surface damage is not catastrophic collapse. Asterisk asterisk. Even under long exposure, HF is more likely to create dull patches, fragile spots, microscopic pitting, whitening, brittleness over time, but it will not cause a bathtub to fall through the floor within hours. It's the difference between termites and dynamite. One weakens structure slowly. The other obliterates. HF is a termite. Hollywood made it dynamite. If the bathtub wouldn't collapse, what would actually happen? Let's imagine the real scenario. You have a ceramic-coated bathtub, a body, a large volume of HF, several hours of contact, poor ventilation, zero professional chemical handling precautions. This is what you'd actually expect. 1. The enamel coating begins to dull and degrade. No Hollywood bubbling, no smoke, just subtle surface damage. 2. Tiny, invisible pits begin forming. These weaken the structure very slowly. 3. The underlying cast iron remains mostly unaffected. In reality, plain iron doesn't react fast with HF. It corrodes slowly, but does not catastrophically collapse. 4. The bathroom becomes lethally toxic. HF fumes accumulate. The room becomes hazardous not because things are dissolving, but because the air itself becomes deadly. Anyone entering without protection is risking lung damage, systemic poisoning, cardiac issues, burns from inhaled HF vapor. This is the horror that TV didn't show. 5. The body begins to partially decompose, but not melt. Skin may discolor. Some tissue may soften. Bones remain largely intact. Fat barely reacts. Hair, nails, cartilage all remain. 6. The bathtub becomes stained, weakened, but not destroyed. This is the biggest mythbuster of all. The tub would still be there. Damaged, yes, but not on the first floor. 7. The floor remains structurally sound. HF would not seep through tile, wood, underlayment, and joists in hours. At worst, there would be some dripping fluid, staining, gradual weakening over days or weeks, but no sudden collapse. Hollywood took far more liberties than most people realize. Why the scene still works dramatically? Here's the irony. Scientifically, the scene is extremely inaccurate, but dramatically is brilliant. A collapsing bathtub full of liquefied organs is visually shocking, unforgettable, darkly comedic. A turning point for Walt and Jesse. A symbolic collapse of Jesse's innocence in bathroom. It sets the tone for the entire series. Chemistry is powerful, but you have to know what you're doing. The actual scientific reality is less spectacular, but far more sinister. In real life, HF wouldn't melt your house. It would kill you quietly, invisibly, and internally. That's not Hollywood exciting, but it is chemically horrifying. Why the floor wouldn't collapse? The real structural physics. To understand why the bathtub collapse in Breaking Bad is scientifically impossible, we need to step out of the chemistry lab and into the world of structural engineering. Because surprisingly, the most unrealistic part of the entire scene isn't the acid, it's the floor. Let's begin with the truth most homeowners never think about. A modern floor is built to handle enormous stress, far more than the weight of a bathtub, a body, or even a tub filled with acid. Floors don't just sit there waiting to snap. They're supported by a network of joists, thick wooden beams, designed to carry thousands of pounds of load while distributing that weight evenly across the structure. To collapse through a floor, you'd typically need years of rot, violent impacts, structural fire, termite destruction, or a dramatic failure in load-bearing members. What you would not need, and what absolutely would not cause collapse, is a weakened enamel coating on a bathtub. Here's the key. Even if the tub failed, the floor wouldn't. A bathtub sits on the floor, not in it. Even if HF somehow destroyed the enamel surface, the cast iron shell underneath would still remain intact. Even if, hypothetically, HF began eating through the cast iron, which it wouldn't, At any significant speed, the liquid would spill out into the tub's interior first, not down into the floor. Only after the tub failed completely would the liquid begin touching the tile and subfloor. And even then, the layers beneath it are not made of materials HF aggressively attacks. Wood? HF doesn't dissolve it. Ceramic tile? Minimal reaction. Cement backer board? No meaningful reaction. In other words, the underlying structure of the house is practically immune to HF's slow and selective chemistry. But let's push this even further. Imagine the absolute worst-case scenario. The tub cracks. The contents spill everywhere. The floor becomes soaked with a mixture of acid and biological fluid. Could the floor then buckle under the weight? Unlikely. Wood absorbs moisture slowly, and HF doesn't chemically destabilize it. It may discolor, it may weaken very slightly over long exposure, but collapse? No. The joists beneath the floor would still bear the load perfectly well. The idea that this fluid mixture would somehow dissolve tile, wood, subfloor, joists, drywall, and ceiling beams in a matter of hours is chemically impossible. To put it into perspective, a wooden floor can usually hold 2,000 to 5,000 pounds of distributed weight. A filled bathtub weighs around 300 to 500 pounds. Add a body, maybe another 150 to 200 pounds. Add acid, another 100 to 150 pounds. You're still at less than half of the load capacity. For the floor to collapse, you'd need either a violent impact force, like dropping a massive object, or long-term structural degradation. A slow chemical reaction in the bathtub simply cannot replicate the sudden force required. The only way an HF-induced collapse could occur is if the floor joists were entirely replaced with components made of silica glass, which of course they are not. Wood, composite materials, and metal fasteners remain structurally sound in the presence of HF. And remember, HF doesn't magically travel downward. It stays where gravity places it. It pools. It spreads. It does not tunnel. Now imagine the scene through the eyes of a structural engineer visiting Jesse's house afterward. They would find a stained bathtub, etched and visibly damaged, tiles dulled or whitened, areas where the acid had pooled leaving discoloration, some corrosion marks on metal fixtures, possibly even slight warping of vinyl surfaces. But the joist? The beams? The load-bearing structure beneath the bathroom? Untouched, structurally identical to before. To collapse a floor, the most dangerous thing in the room wouldn't be HF. It would be ignorance, bad construction, or gravity acting through traumatic force. The irony is that the only real danger in the entire scenario is breathing the air. HF vapor is so toxic that simply entering the bathroom could kill someone. But the house itself, the beams, the joists, the load-bearing structure, would remain solid, indifferent to the panic unfolding inside. For all the shock, all the visceral horror, all the unforgettable ooze dripping from floorboards in Breaking Bad's legendary bathtub scene, there's a quieter truth hiding underneath. Fiction doesn't just bend science. Sometimes it outruns it at full sprint. And in the case of hydrofluoric acid, it doesn't just outrun it, leaps off a cliff. Because here's the wild paradox. The show dramatically overplays HF in ways that make chemists cringe, yet it simultaneously underplays how profoundly dangerous it really is. It turns the acid into a Hollywood monster, a magical sludge maker that dissolves everything in its path, except the things that would actually be destroyed in real life. And the result? A scene that is iconic, memorable, meme-worthy, and scientifically upside down. This is where we peel back the final layer of the hydrofluoric acid myth. The layer no one talks about. The part where chemistry stops being entertainment and becomes a chilling lesson in what HF really does and what it absolutely does not do. Because if someone walked into Breaking Bad having never heard of hydrofluoric acid before, they would leave thinking of it as a destructive supervillain. In reality, HF is less about dramatic melting and more about stealth damage. Pain delayed, tissue destruction hidden, bone loss silent, No instant liquefaction. No cartilage soup. Just a quiet, deadly chemical that eats calcium the way fire eats oxygen. So, in this final segment of Chapter 1, we explore the crossroads between fact and fiction, the place where the show's exaggerated spectacle meets the terrifying subtlety of actual hydrofluoric acid exposure. If the bathtub scene is the loud story, this is the quiet one, and as you'll see, the quiet one is far more unsettling. Let's begin with one of the most misunderstood ideas, the speed of destruction. In the show, Jesse pours HF, walks away, and minutes later we get catastrophic failure, metal fixtures collapsing, the ceiling turning into soup, everything dissolving like sugar in a hot drink. In reality, HF destruction is not instantaneous. Even strong acids don't melt materials instantly. Sulfuric acid, hydrochloric acid, nitric acid, they all require contact time and specific conditions to produce visible destruction. Hydrofluoric acid is no different. It attacks over minutes, hours, sometimes even longer depending on concentration. It doesn't cause catastrophic collapse the way TV imagines because chemistry is not a cartoon. The universe is a patient artist, not a vandal. But here's the twist. HF does do something far more disturbing, something the show never depicts. Even though it's the most dangerous property the chemical has, HF penetrates deep into tissues, binding to calcium and magnesium in the body, shutting down nerves, disrupting cell function, and potentially triggering cardiac arrest even before you feel significant pain. That means the real horror of HF isn't what you see, it's what you don't see. No bubbling flesh, no melting skin, no dramatic sizzling. The person might not even know how severe the exposure is until it's too late. In fact, the greatest danger from HF is systemic toxicity, not surface burns. If even a small amount is absorbed, your blood chemistry changes, your nervous system misfires, your heart rhythm destabilizes, and death can occur silently, hours later. That is the real threat, not the cinematic meltdown of a bathtub. And that brings us to the physical environment, the bathroom itself. Even though HF wouldn't melt the tub clean through the floor the way the episode portrays, an HF spill would still be a serious, life-threatening event requiring evacuation, hazmat intervention, and structural safety checks. The fumes alone, hydrogen fluoride vapor, can cause deep lung burns that progress long after exposure. The water supply pipes, drain systems, adhesives, and structural joints could be compromised, not because HF melts them, but because it corrodes, weakens, and destabilizes materials over time. It's not explosive destruction, it's chemical sabotage. But the show wasn't wrong about everything. They were right about one thing: hydrofluoric acid is not to be messed with. Even though it won't eat a bathtub in 30 minutes, its real power is arguably more terrifying. And perhaps in a strange roundabout way, the show did something good by mythologizing it. It made people curious. It made them ask questions. And curiosity is the gateway to understanding. And as we close this chapter, we step out of the bathroom and into the wider world of Breaking Bad science. Because if this is how the show handled one of its most infamous moments, imagine how it handles explosives. Imagine how it treats unstable compounds, pressure waves, detonation physics, and the line between bang and boom. That's where we're headed. Next stand, the gap between Hollywood and reality is about to get even wider. Chapter 2, Part 1. Fulminated mercury. The myth, the shock, and the science behind the crystal bomb ***. There's a moment in Breaking Bad when chemistry stops being a quiet discipline and becomes a weapon. A moment when Walter White, cornered, underestimated, and humiliated, steps into Tuco Salamanca's office with nothing but a bag of crystal and the calmest expression ever worn by a desperate man. What happens next has burned itself into television history. Walter throws a single shard onto the floor, and the room detonates with a thunderous blast that shatters every window, knocks Tuco and his men off their feet, and fills the air with a cloud of raw intimidation. It is one of the most badass displays of chemistry ever filmed. But how close does this come to reality? What would really happen if someone walked into a building with a bag of fulminated mercury crystals? Could a single piece really explode like that? Could you throw it? Would you even make it to the door without the entire bag detonating in your hand? And most importantly, what is fulminated mercury actually capable of in the real world? This chapter begins with the exact moment Walter tosses the crystal. The instant physics meets storytelling. Because fulminated mercury, as dramatic as the show makes it, is not a fantasy chemical. It is very real, very unstable, and historically significant in the world of explosives. It has been used in detonators, percussion caps, early blasting technology, and even in military primers. It's delicate, temperamental, easily shocked, and notoriously unreliable. One wrong vibration, one accidental impact, one unexpected friction event, and fulminated mercury doesn't ask questions. It simply reacts. But does that reaction look anything like the explosion we see in Breaking Bad? That's where the physics becomes fascinating. Fulminated mercury doesn't detonate with the power of TNT or C4. It's not a building-leveling explosive. It's a primary explosive, a compound designed to initiate larger, more powerful charges. Its job is not to create massive destruction. Its job is to trigger the substances that do. You use it to ignite dynamite, not replace it. Its explosive force is sharp, sudden, localized, a violent chemical snap rather than Hollywood thunder. And that's where the show bends reality, just enough to thrill you, without completely abandoning scientific backbone. In truth, a room-filling explosion from a single crystal would require orders of magnitude more energy than fulminated mercury can provide. The shockwave alone in the show's scene is closer to what you'd expect from a significant quantity of a high explosive like petin, RDX, or nitroglycerin. Fulminated mercury is similar in sensitivity, but not in power. Yet here's the thing, the show didn't get everything wrong. In fact, they got many qualities right. Fulminated mercury is crystal-like. It is dangerously unstable. It can detonate on impact. And it has a storied history as one of chemistry's most unpredictable creations. So, while the blast radius is exaggerated, the underlying principle chemistry as controlled violence is grounded in truth. But let's pull the camera back for a moment, because to really understand Walter's moment of chemical dominance, we have to go deeper than the scene itself. We have to look into the history, the structure, and the terrifying temperament of fulminated mercury. This is a compound discovered more than 2 centuries ago, long before modern explosives research, yet powerful enough to reshape entire industries. It has ignited guns, launched engineering projects, and accidentally killed chemists who pushed their luck one step too far. It is a material that demands respect, and historically, it has earned that respect through devastation. So Chapter 2 begins with the truth that's more compelling than fiction. Fulminated mercury is not Hollywood magic. It's a real reminder of how explosive chemistry can be when mishandled. And while Breaking Bad amplifies its destructive capability for dramatic effect, the instability of the compound itself is every bit as terrifying as the show suggests. Inside the crystal, why fulminated mercury is one of chemistry's most temperamental explosives ***. If you want to understand why the fulminated mercury scene in Breaking Bad is both brilliant and scientifically broken, you have to start inside the molecule itself, because the danger of this compound isn't its size, or its color, or even its crystalline form. The danger is hidden in the structure, in the way its atoms cling together like a fragile truce waiting for the faintest excuse to collapse into violence. Fulminated mercury, chemically written as HgCnOa, is what chemists call a primary explosive. That phrase alone tells you something important. It's not designed for power. It's designed for sensitivity. A primary explosive is the chemical equivalent of a hair trigger, something that detonates easily so it can set off a more stable, more powerful secondary explosive. Think of it as the spark, not the flame. The nudge, not the punch. Its entire purpose is to explode from triggers other chemicals would shrug off. And that sensitivity comes from its internal tension. The fulminate group attached to the mercury atom is stretched thin. It's energetically unstable, like a badly balanced stack of books that looks fine until you breathe too close to it. The carbon, nitrogen, and oxygen atoms arranged in the CNO fulminate ion don't particularly want to sit together in that configuration, and they certainly don't want to sit attached to a heavy metal like mercury. Every bond in the molecule exists under stress, subtle, invisible, but crucial. If molecules had emotions, fulminated mercury would be described as nervous. That nervousness is why the compound reacts violently to things that normally don't matter. A tap, a scrape, a crystal drying too quickly, a jar being moved, a spoon hitting glass, a small miscalculation in synthesis. Even temperature changes can push it past the edge. This isn't Hollywood exaggeration. It's historically documented chemistry. Chemists in the 1800s called this substance mercury fulminate, and they learned early, sometimes the hard way, to treat it like a loaded weapon with no safety switch. And that brings us to the first major flaw in the Breaking Bad depiction. Nobody in their right mind carries a bag of fulminated mercury crystals. Not in a pocket, not in a backpack, not in a plastic baggie, not anywhere that involves movement, friction, or gravity. The amount of vibration caused by simply walking into a building would be enough to risk detonation. The idea of a grown man tossing a chunk onto the floor? That borders on the suicidal. But let's pause here, because this is where things get interesting. The myth isn't that fulminated mercury explodes on impact. It can. The myth is in the degree of explosion, the scale, the spectacle. Fulminated mercury is incredibly sensitive, yes, but its detonation is sharp and localized. It produces a violent shock wave in a small radius, enough to rupture eardrums, injure hands, or destroy delicate objects nearby. But leveling an entire room the way the show portrays? That's where Hollywood makes its move. To understand why, picture a firecracker versus a stick of dynamite. Firecracker can go off in your hand and cause serious injury. It can tear flesh, damage fingers, send fragments everywhere, but it won't knock down a wall. For that, you need a secondary explosive, something with more mass, more stable stored energy, more sustained output. Fulminated mercury is the firecracker, not the dynamite. Where the show does get deserved credit is in its attention to detail. Vince Gilligan and his science advisors deliberately chose a real explosive compound rather than invent a fictional chemical. They understood that explosive crystals do exist, and that fulminated mercury was the earliest historically significant detonator material. So, while the magnitude is exaggerated, the foundation is surprisingly legitimate. But here's the real twist. Even though the explosion in the show is scientifically inflated, the danger of handling that amount of fulminated mercury is actually underplayed. Walter White walks calmly into the room, slams the bag on a desk, gestures dramatically, raises his voice, and throws a crystal with theatrical precision. In reality, the simple act of setting down the bag could have detonated it. The friction of the crystals rubbing against one another could have been enough. Even the tension of Walter's fingers applying pressure while holding the bag could have set it off. So the explosion is too big, but the survival leading up to it is far too easy. Now let's talk about why. If Walter had brought a realistic amount of fulminated mercury, say, several grams, that alone would be unreasonably dangerous. If he had brought what appears in the show to be hundreds of grams, the situation becomes impossible. There is no physical way a bag of that quantity could be carried safely. Fulminated mercury is never stored in bulk. In fact, explosive manufacturers historically avoided making larger batches because even slight variations in crystal size or dryness could destabilize a whole container. But here's a fascinating layer. While the show exaggerates the explosion, it's still rooted in a fundamental truth, the idea that chemistry, even small amounts of it, can be powerful in ways the untrained eye doesn't expect. Fulminated mercury isn't a Hollywood invention. It has killed chemists. It has destroyed laboratories. It has triggered countless accidents before safety protocols existed. It was used in percussion caps because it detonates reliably under mechanical impact. And even today, old, forgotten ammunition loaded with mercury fulminate can still pose a danger because of the compound's long-term sensitivity. So the show's mistake isn't choosing fulminated mercury, it's misunderstanding its character. In Breaking Bad, the chemical behaves like a Hollywood explosive, stable until deliberately triggered. In real life, it behaves like a temperamental sleeping dragon, unpredictable, excitable, and prone to waking up violently if disturbed. The moment of detonation. What actually happens when fulminated mercury explodes ***. To understand why the Breaking Bad explosion is both thrilling and scientifically distorted, we need to travel into a time scale so small it barely feels real, into the microsecond world where molecules rearrange themselves faster than thought, faster than reflex, faster than fear. Because when fulminated mercury detonates, the entire event, the shock, the rupture, the release of gas and heat unfolds in the tiniest fraction of a blink. Every explosion begins with a disturbance, but for fulminated mercury, that disturbance can be almost insultingly small. A tap, a scrape, a vibration, something that wouldn't matter to most materials, something that doesn't even register to the human body. But to this compound, it's a trigger and invitation for instability to take control. The fulminate ions, already under internal strain, don't need a dramatic cause. They need a suggestion. And the moment that suggestion arrives, the molecule collapses. Imagine this. The crystal fractures. One bond snaps. A single atom shifts position. A microscopic region heats by a fraction of a degree. And suddenly the entire molecular lattice destabilizes. In real explosives, this is called initiation. And for a primary explosive like mercury fulminate, initiation is the beginning of the end. What happens next is where chemistry becomes violence. The fragile bonds holding the fulminate together rupture in a chain reaction, so fast that we lack words to describe it at human scale. The breakdown produces an immediate release of hot, expanding gases, carbon monoxide, nitrogen, metallic mercury vapor, and a burst of heat intense enough to create a shock wave. But shockwave doesn't mean what Hollywood portrays. It doesn't mean a rolling, thundering burst that levels buildings and shatters rooms. It means a sharp pressure spike, brief, concentrated, locally devastating, more like the crack of a gun than the roar of a bomb. This is the key difference between primary and secondary explosives. Primary explosives like fulminated mercury detonate quickly, violently, but not massively. They have extremely fast energy release but limited total energy. Secondary explosives like TNT or RDX release more energy over a slightly longer duration, producing the much larger blast effects associated with demolition or warfare. Fulminated mercury isn't built for power. It's built for precision. It's not a bulldozer, it's a spark plug. To make this clearer, imagine popping a balloon versus crashing a car. A balloon bursts instantly, fast, loud, and startling, but the total energy involved is small. A car crash is slower but involves vastly more force. Fulminated mercury is the balloon, instantaneous, sharp, high velocity, but limited in scope. So what would happen if Walter White threw a crystal of pure mercury fulminate onto the floor of Tuco's office? Here's the reality. If the crystal detonated, and yes, throwing it could absolutely set it off, the immediate effect would be a small but violent localized explosion. It would almost certainly rupture eardrums, send shrapnel-like fragments of crystal and flooring flying, damage the hand or arm of anyone nearby, and potentially ignite small nearby materials. But it would not shatter multiple windows across a building. It would not create a Hollywood shock front that throws grown men across a room. And it would certainly not produce the cinematic blast radius depicted on screen. If anything, the danger would be to Walter himself. The moment he threw it, the recoil shock, the proximity to the detonation, and the fragment spray could have seriously injured him. Fulminated mercury doesn't politely wait until it hits the correct target. It detonates the instant the crystal's internal stress gives out. But here's the nuance. Scaling matters. The amount shown in the bag, it truly were fulminated mercury, would amount to a walking suicide vest of catastrophic proportions, but not in the way Breaking Bad shows. It wouldn't produce a huge blast, it would produce dozens of tiny detonations inside the bag itself. Each individual crystal acts as its own micro-explosive, which means that if the bag ever detonated, it would be chaotic, splintered, and fatal. The crystals would go off in something like a chain reaction, shredding the person carrying them and anyone within a few meters, not throwing them across the room, tearing them apart. This leads to a subtle, dark irony. Breaking Bad exaggerates the destructive force of a single crystal massively, but drastically underestimates the lethality of carrying a bag full of them. There is no universe, fictional, scientific, or miraculous, where a man walks calmly through a doorway with a sack full of one of the universe's most sensitive primary explosives. Most chemists wouldn't walk across a room holding a gram in a reinforced container. Walter walks into a gang hideout with enough to destroy himself 10 times over. It's poetic fiction, but impossible chemistry. Still, the essence of the scene, the idea that a smart man with chemistry, knowledge, can weaponize the sensitivity of fulminated mercury is grounded in truth. This compound has been used in countless detonators because it does do exactly what Walter demonstrates. It responds to impact with self-amplifying violence. But the scale, the magnitude of destruction, the blast radius, the cinematic shock wave, that's where storytelling takes the wheel and drives off the map. The physics of blast waves, why Hollywood explosions don't behave like real ones, asterisk, asterisk. To truly understand why the Breaking Bad explosion looks the way it does, and why real fulminated mercury would behave so differently, we need to step into a world where force moves faster than sound, where pressure becomes a weapon, and where the air itself turns into a momentary hammer. This is the physics of blast waves, and it's one of the most misunderstood concepts in all of television. Every explosion, from a tiny firecracker to a demolition charge, produces a pressure wave, a sudden jump in air pressure that propagates outward from the detonation point. But the shape, strength, and speed of that wave depend entirely on the energy released. And that's where Breaking Bad takes artistic liberty. In the show, when Walter throws the crystal, the resulting blast fills the room like a thunderclap, shatters windows across multiple walls, knocks Tuco and his crew off their feet, and covers the room in dust. The air expands violently, almost like a CGI ripple, as if the entire space momentarily becomes a balloon popping from the inside. It makes for incredible TV, but it's not how blast physics works, certainly not with fulminated mercury. Let's break the scene down using real physics. 1. The shockwave must have enough energy to move air massively. A human being weighs anywhere from 70 to 100 kilograms. To physically lift a person off the ground with a shockwave, you need enormous overpressure, a level only reached by high explosives in significant quantities. Fulminated mercury, while intensely sensitive, doesn't store much chemical energy. Its detonation velocity is high, but its total available power is small. Enough to rupture eardrums or injure limbs? Yes. Enough to fling multiple adults backward? Absolutely not. Throwing someone with a shockwave is rare even with military explosives unless very large amounts are involved. In most real explosions, the shockwave injures people, not by tossing them, but by rupturing lungs, bursting blood vessels, and damaging organs. Hollywood favors the dramatic over the accurate. 2. Window shattering requires pressure, a lot of it. Glass breaks when the overpressure reaches a threshold of around 1 SI. That sounds small, but generating even that pressure over an entire window takes considerable energy. A single gram of fulminated mercury can shatter a small glass container nearby, but to break multiple room-sized windows simultaneously, you would need either a secondary explosive charge, a tightly confined detonation chamber, or a far more powerful explosive material. Fulminated mercury is a detonator, not a demolition charge. The Breaking Bad scene behaves like someone set off several hundred grams of petin or a stick of dynamite, not a small crystal. 3. The room should fill with smoke, but not like that. Real detonations produce particulate matter, vapor, and hot gases. But the cloud in the TV scene behaves almost like dust shaken off furniture, a slow floating haze rather than the tight plume expected from primary explosive detonation. Mercury fulminate releases toxic mercury vapor, nitrogen oxides, and carbon monoxide, none of which appear visually in large dramatic clouds. The show relies on standard Hollywood dust effects to amplify the impact. Real chemistry is invisible. Fiction makes it visible. 4. Humans don't fly, they crumple. The most unrealistic part of Hollywood explosions is the body launch. In reality, a shockwave hits the body too fast to throw it backward. The force distributes over the surface area, and the result is more like being punched everywhere at once. People generally collapse where they stand. Yet in Breaking Bad, Tuco goes flying as if struck by a telekinetic wave. The physics simply doesn't support this with the explosive used. 5. The bag itself would never survive. This is the biggest deal breaker. A sack of crystalline, fulminated mercury, even a fist-sized amount, would behave like a constellation of tiny bombs packed together. If one crystal detonated, the others within immediate proximity would follow almost instantly. This wouldn't create a single large dramatic boom. Instead, it would create a chaotic, lethal micro-detonation chain reaction strong enough to shred the bag, destroy the handhold in it, and likely kill the carrier. Walter wouldn't walk out of that room. He wouldn't walk into it. The bag would have exploded long before the confrontation. Yet the scene plays out as if the crystals are unnervingly stable until deliberately thrown, as though they are Hollywood impact grenades that only go off when dramatically hurled at the ground. Real fulminated mercury doesn't care about timing or narrative tension. It cares about instability. 6. Pressure doesn't work like a movie sound effect. Hollywood often exaggerates how explosions sound. In real life, small primary explosives create a sharp crack, a high-pitched snap, or a loud but extremely brief bang. Not a thunderous bass-heavy boom reverberating through an entire building. Breaking Bad uses sound to sell spectacle, even if the blast power wouldn't match that acoustic profile. So what would the real explosion look like? If Walter tossed a real fulminated mercury crystal onto Tuco's floor, the actual result would likely be a blinding flash, a deafening pulse, a small crater in the floor, possibly fragments embedded in nearby walls, immediate panic, eardrum rupture within a few feet, but not whole room destruction. It would be terrifying but small. It would be deadly but localized. It would be impressive but not theatrical. Hollywood wants spectacle. Chemistry offers precision. The real chemistry of controlled explosives. And what Walter should have used ***. Now that we've dissected the physics, the molecular instability, and the Hollywood distortions behind the fulminated mercury scene, we can finally confront the central question this entire chapter has been building toward. If Walter White wanted to pull off something scientifically believable, what explosive material should he have used instead? And how would a real chemist weaponize it without instant self-destruction? 'Cause here's the truth, the show chose the wrong chemical for the right idea. And the reality of controlled explosives is far more fascinating and far more dangerous than fiction dares to explore. To understand this, we need to step inside the world of explosive engineering, where chemistry becomes choreography, where the goal isn't chaos, it's control. Every demolition, every blast cap, every military charge, every detonation device is built on the same principle. Unstable materials are never used directly. They are buffered, shielded, moderated, and isolated. A real chemist never walks into a building with a bag full of a primary explosive. That's not bravery, that's a death wish. Instead, the most dangerous chemicals on Earth are used in quantities measured in milligrams, not handfuls. Which brings us to one simple truth. If Walter truly wanted a handheld explosive tool, he would need a secondary explosive, something powerful but stable enough to carry. TNT, PTN, RDX, HMX. These are materials that don't detonate from simple impact or handling. They require a proper detonator and a carefully controlled triggering mechanism. They don't explode when dropped. They explode when told. That's exactly why they're used in the real world instead of temperamental primaries like mercury fulminate. But a secondary explosive alone isn't enough. It needs a detonator. And that's where fulminated mercury historically earned its place as the backbone of explosive technology. It's not a main charge, it's the spark that triggers something stronger. If Walter had wanted a realistic explosive scene, the scientifically accurate approach would have been something like this. A small, well-contained blasting caps, something the size of your thumb, containing a milligram scale quantity of fulminated mercury, connected to a reliable secondary explosive charge. Small, safe to carry, powerful enough to shatter windows or blow open a door, and actually believable. But Breaking Bad needed spectacle, not plausibility. So, instead of a blasting cap, Walter strides into Tuco's office with what looks like several hundred grams of a notoriously unstable primary explosive in a bag, something no chemist, no bomb maker, and no demolition expert would ever dare come near. Let's talk about how chemistry handles this in the real world. The entire field of explosives is built on mitigating risk. Sensitive primaries are always used in tiny quantities, encased in metal housings, separated from friction, vibration, and environmental triggers. Engineers isolate them deliberately so they only detonate when required. The blasting cap provides the initial shock. The secondary explosive amplifies it. This layered structure is what allows modern demolitions and munitions to be both powerful and predictable. If Walter wanted to bluff Tuco realistically, he could have walked in with a small device containing a real-world primary explosive, like lead azide, lead stiffnate, or mercury fulminate, embedded in a stable secondary charge. The threats would be credible, the explosion if triggered would be devastating, and more importantly, he might have actually survived the process. But Breaking Bad chose drama over accuracy. And in doing so, it missed an opportunity to demonstrate something far more interesting, the genius of controlled chemistry. A real chemist doesn't rely on unstable crystals tossed like marbles. A real chemist relies on structure, safety, precision. They build devices the way an engineer builds a clocked elegant, measured, balanced. The idea that Walter, an accomplished chemist, would risk his life walking around with bulk mercury fulminate is the single greatest scientific contradiction in the entire series. Now let's go deeper. If Walter had used a realistic explosive substitute, say Petin or RDX, he could have carried enough to destroy the office without risking spontaneous detonation. These materials require a detonator to explode. They are stable under pressure, friction, and heat to a degree that makes them safe enough to transport. They're not toys, but they are manageable. And if Breaking Bad wanted a middle ground between science and spectacle, Petin would have been the perfect choice. It's white, crystalline, powerful, and far more believable as something that could level a room with the right detonator. But that's the key, no detonator, no explosion. And that's why the fulminated mercury scene, as shot, would never work. Walter throws a crystal and gets a room-shaking blast. In reality, without a secondary explosive behind it. A primary explosive simply doesn't have enough stored chemical energy to produce such destructive force. It's like expecting a matchstick to level a house. There's also the question of survivability. If Walter had carried a realistic, stable explosive in a reinforced container, he would have walked in safely and left safely, still bold, still dramatic, but scientifically plausible. Instead, the show trades realism for visual punch. Walter becomes a walking contradiction, a brilliant chemist making the most reckless chemical decision possible. And yet that's what makes the scene iconic, not accuracy, emotion. So here's the truth distilled to its simplest form. Walter White could have made a bomb. He could have made a realistic one. He could have used chemistry to intimidate Tuco in a scientifically accurate way. But he could not have walked into that office with raw fulminated mercury crystals and lived long enough to speak a single line. When we think about instability in chemistry, most people imagine red wires and blue wires, timers counting down, sparks threatening to fly. But instability, true instability, is rarely dramatic in appearance. It's quiet, invisible. It doesn't glow. It doesn't pulse with light like a sci-fi reactor core. It simply exists in a state of tension, a molecular arrangement waiting for the wrong moment, the wrong touch, the wrong vibration. And this is where fulminated mercury lives, perched between order and chaos, one gentle step away from a reaction that is as unpredictable as it is unforgiving. To understand just how risky this compound truly is, we have to first step away from the Hollywood version, where danger is exaggerated, stylized, or made theatrically controllable, and instead step into the far more sobering reality of explosive chemistry. Fulminated mercury, chemically written as HgCNOA, is a primary explosive. But unlike secondary explosives such as TNT, PETN, or RDX, which require a detonator to set them off, a primary explosive reacts violently to the smallest stimulus. A scratch, a tap, a change in temperature. Even the friction of a shaking container can be enough to provoke a catastrophic reaction. But despite this sensitivity, the explosive power of fulminated mercury is nowhere near the cinematic force depicted in Breaking Bad. It is not a demolition-grade explosive. It is not built for destruction. Instead, it is historically used to trigger other explosives, because it releases energy very quickly, but not in enormous quantities. Its value lies in its speed, not its strength. And this distinction matters, because the difference between the show's exploding office scene and the behavior of fulminated mercury in real life is the difference between throwing a large firecracker and throwing a hand grenade. To get a sense of the true magnitude, imagine this. A crystal of fulminated mercury the size of a sugar cube would be dangerous to handle, certainly capable of injuring hands and eyes, possibly even causing fatal wounds if detonated directly against a person. But it would not produce a pressure wave strong enough to shatter structural walls or send furniture flying in all directions. It might fracture glass nearby. It might create a sharp concussive sound. But a room-destroying blast? That crosses into the realm of fiction. The show takes this compound, which is already hazardous enough on its own, and elevates it to an almost supernatural force. A single crystalline grenade capable of leveling a space with cinematic precision. The real physics behind that scene tell a different story. One grounded not in spectacle, but in the cold calculations of pressure, volume, and energy release. Instead of a shockwave that sweeps through an entire building, a real fulminated mercury detonation would be localized, sharp, violent, but small, dangerous to the handler. Not devastating to the room. Still, that doesn't mean the compound is safe. Far from it. One of the ironies of explosive materials is that weaker does not mean less dangerous. Fulminated mercury is infamous among chemists for being unpredictable. Even the process of making it is a gauntlet of risk. Historical accounts describe chemists and munitions workers losing fingers, hands, and even entire limbs because the compound can detonate spontaneously during synthesis. The instability is intrinsic to its molecular structure. Carbon, nitrogen, and oxygen arranged in tension, bonded to a heavy metal atom that amplifies the reaction's violence. Think of it like a mousetrap permanently cocked, permanently ready, waiting for the faintest provocation. And unlike many modern explosives, fulminated mercury is old-fashioned. It lacks the refinements and stabilizing techniques developed over the last century. It is chemistry from a time when workers wore wool coats, not blast-resistant gear, when safety standards were improvisational, when losing a digit was seen as an occupational hazard. So even though it doesn't pack the Hollywood punch of TNT, Its volatility makes it terrifying in a different way. You can't predict what will set it off. Another crucial factor the show overlooks is quantity. In Breaking Bad, Walter tosses a handful of glass-looking crystals, implying that the mass alone is enough to create a huge blast. But in reality, the yield is proportional to the amount used. 100 grams of fulminated. Mercury is extremely dangerous to handle, but still not capable of producing the type of building, shaking explosion shown on screen. The show makes it appear as though a single large crystal is somehow more powerful than the same mass broken into smaller pieces, which is physically inaccurate. Explosives don't work like that. The chemical energy stored is based on total mass, not shape or theatrical appearance. In fact, larger crystals of primary explosives are more dangerous to handle because internal defects, impurities, or stresses can cause spontaneous detonation. But their explosive strength isn't multiplied simply because they're in a single piece. The show uses this large crystal cinematography as a visual metaphor, something striking, something memorable, but the science behind it doesn't hold. If we dig deeper into the physics of detonation, we see another mismatch. True detonations propagate via a supersonic shock wave traveling through the material. Primary explosives like fulminated mercury often undergo deflagration, a rapid burning, rather than a true detonation. Only under specific conditions, sufficient confinement, precise impact, and appropriate crystal size will it transition into a full detonation. Most of the time, it burns violently, and when it does detonate, the pressure wave produced is extremely short-lived and highly localized, lacking the sustained force needed to tear apart structural materials like drywall, concrete, or metal supports. This detail, while highly technical, is one of the clearest indicators that the show's depiction leans heavily into artistic license. They needed a betrayal of expectations, something surprising and theatrical, so they took the name of a real explosive and adjusted its behavior to fit the scene. Perhaps the most important scientific correction is this: fulminated mercury is not something you could casually store in a bag, carry across a room, or dramatically throw against the ground with theatrical force. In real life, even jostling such crystals would risk accidental detonation. The scene where Walt tosses them like candy-coated pebbles is one of the most physically unrealistic actions in the entire series. Not because the explosion is impossible, but because the journey to the explosion is impossible. The compound wouldn't wait politely for the dramatic moment. It would detonate long before the monologue finished. In reality, handling primary explosives requires tools designed to minimize shock, friction, and static electricity. Even glass equipment is often avoided because a misplaced tap could trigger an accident. So the idea of a man confidently pacing with a bag full of this material is, scientifically speaking, about as risky and unlikely as juggling live grenades with missing pins. One more twist often overlooked is toxicity. Mercury compounds are not just explosive, they are profoundly poisonous. Even small amounts can be absorbed through the skin or inhaled as vapor, leading to severe neurological damage. This means that even if fulminated mercury didn't explode on contact, handling it bare-handed would be a slow and painful form of self-destruction. The show's focus on dramatic force overlooks the equally dangerous, equally real, equally horrifying chemical risks that come with the substance. The science becomes even more grim when we consider that prolonged exposure could lead to tremors, cognitive decline, and organ damage. In short, Walter White, the hyper-precise chemist, would know better than anyone how suicidal it would be to casually carry and throw this substance. And yet the show uses this moment not to educate but to entertain. And that's okay. Storytelling has different priorities than chemistry. But when we pull back the curtain and examine the real physics, the real chemistry, and the real explosive behavior, we discover something far more interesting than the Hollywood version. The truth is less cinematic but more dangerous. It reminds us that science doesn't need exaggeration to be terrifying. It doesn't need special effects to be dramatic. The facts alone, quiet, invisible, molecular, carry enough weight to reshape our understanding of risk. And as we continue through this documentary, one theme becomes increasingly clear. Breaking Bad doesn't just take liberties with chemical accuracy. It transforms real science into theater. And while the results make for unforgettable television, the real world operates with rules far less forgiving. Chapter 3. Purity and Potency. The Blue Meth Conundrum. In the modern mythology of television, few props have become as iconic as Walter White's crystalline blue methamphetamine. It is more than a fictional drug. It is a symbol of power, of transformation, of pride, of obsession. When people think of Breaking Bad, they think of that blue sparkle, the glow of an illegal product elevated to something almost supernatural. But behind the cinematic shimmer lies a powerful misconception that purity is visually obvious, that color equals quality, that chemistry behaves in ways that are aesthetic, dramatic, and neatly symbolic. Reality, however, is far less accommodating. In real chemistry, purity does not shine with a color-coded badge of honor. It does not conveniently manifest in blue, nor does it create a product so visually perfect that it resembles handcrafted gemstones. To understand how far the show bends the science, we have to first examine what purity actually means, not in the storytelling sense, but in the chemical sense. Purity in chemical production refers to the absence of impurities, foreign molecules, leftover reagents, competing structures, contaminants, solvents, or byproducts. Purity is measured through analytical methods such as gas chromatography, mass spectrometry, NMR spectroscopy, and melting point analysis. None of these involve simply looking at the product and judging it with the naked eye. Chemistry is not cooking. It is not baking. It is not a craft where a master artisan can say, "Ah yes, this looks right." In reality, a crystal can appear flawless and still contain a cocktail of impurities invisible to the unaided eye. Conversely, a batch of methamphetamine could be nearly colorless and exceptionally pure, and yet look entirely unremarkable. The aesthetic does not reveal the quality. Instead, purity is an invisible, quantitative fact, something only instruments can prove. This is where the first major scientific deviation in Breaking Bad occurs. The show links purity to a distinctive blue color. In real chemistry, methamphetamine is colorless when pure. Crystal meth, in its most refined form, looks like crushed ice white, translucent, sometimes slightly cloudy but never blue. The presence of color typically indicates impurity, not perfection. A blue tint could result from dye, contamination, metal ions, residual solvents, or degradation products. But it would not signify exceptional purity. In fact, it would signify the opposite. If a real chemist produced vividly blue methamphetamine, other chemists would immediately ask, what went wrong? The show flips this logic on its head, turning an impurity into evidence of mastery. And while this works beautifully for storytelling, it dismantles one of the core principles of chemical purity. Perfection is invisible. Another misconception born from this narrative choice is the idea that color equals potency. In real-world drug manufacturing, potency relates directly to the concentration of the active compound, not to color, not to shine, not to the shape of the crystals. The pharmacological effect is determined by the molecule itself, not the hue of the batch. And purity only affects potency if impurities are replacing the active molecule in significant proportions. Once again, this is not visible to the eye. Even trained chemists cannot look at a crystal and determine its concentration. And yet in the world of Breaking Bad, purity becomes a visual spectacle, something that can be seen across the room and judged with immediate certainty. Reality is far more understated. Science does not perform theatrics. It does not prioritize aesthetic drama. It simply follows the laws of molecular interaction. The second major inaccuracy in the show's portrayal lies in the shape and size of the crystals themselves. Real methamphetamine crystallizes in small shards or fragments, depending on factors like cooling rate, solvent choice, and purity. but the massive, glass-like slabs depicted on screen are far larger and more uniform than typical illicit synthesis would ever produce. Large crystals require slow, controlled recrystallization, something difficult to achieve outside a pristine laboratory with proper equipment, climate control, and solvent purity. Homemade clandestine labs tend to produce irregular, inconsistent crystals that are far less aesthetically pleasing. The beautifully symmetrical slabs in the show resemble laboratory-grade crystallization done with professional precision, not quick clandestine production. Once again, the aesthetic has been adjusted for cinematic impact rather than scientific accuracy. But perhaps the most significant inconsistency is the show's claim that Walter White produces methamphetamine at 99.1% purity. While purity can indeed reach the high 90s in controlled lab conditions, achieving this level consistently in a non-sterile, improvised environment is extraordinarily unlikely. Real-world clandestine labs operating with limited equipment, impure reagents, inconsistent temperature control, and unregulated solvents rarely achieve purity above the mid to high 80% range at best. Even highly experienced clandestine chemists with years of practice seldom hit 90% purity, and those who do generally can't reproduce it without access to high-grade precursors and professional analytical tools. Purity fluctuates naturally with batch conditions. With Walter's improvised setups, RV cookouts, desert tents, and makeshift industrial labs, the consistency implied in the show is closer to myth than science. Chemistry is unforgiving. It rewards precision and punishes improvisation. Even the show's iconic 99% pure label raises another overlooked point. Purity does not guarantee safety. High-purity drugs are more dangerous for users, not less. A purer stimulant increases the risk of overdose, cardiovascular failure, addiction, and psychosis. In the real world, the appearance of an unusually pure product often leads to medical crises and fatalities as users underestimate its potency. So while the show frames Walter's achievement as a badge of excellence, a testament to his genius, the reality is far darker. High purity isn't impressive. It's deadly. The idea that Walter's meth is superior because it is blue also reinforces another misconception, that drugs, like high-end wine or artisan cheese, have qualities that can be visually evaluated. But street-level drug culture is not a realm where aesthetics tell the truth. Many additives used by dealers' food coloring, dyes, cutting agents are chosen specifically to create illusions of purity or potency. Users often mistake these visual cues for quality, leading to dangerous assumptions. Breaking Bad cleverly uses this real-world phenomenon, people trusting appearance over chemistry, to weave its narrative, but ironically ends up reinforcing the very myth it was inspired by. In reality, a product's color is meaningless without chemical analysis. A batch of blue crystals could be weak, toxic, contaminated, or laced with substances that have nothing to do with methamphetamine. Blue is not magic. Blue is not quality. Blue is marketing. And yet, despite all the scientific inaccuracies, the idea of blue meth worked flawlessly within the show's universe. It gave Walter White a signature, a brand, a calling card that symbolized his descent into moral collapse. It made the chemistry feel mythic. It created a visual language viewers could instantly recognize. It transformed something ugly and destructive into something that looked strangely beautiful, a deliberate artistic contradiction. This is where storytelling and science part ways. In the narrative realm, the blue crystal is perfect. In the scientific realm, it is an impossibility born from dramatic need. What makes this chapter fascinating isn't simply that Breaking Bad got the science wrong, it's why it got the science wrong. The inaccuracies are intentional, crafted to serve theme, symbolism, character development, and emotional impact. The meth isn't blue because chemistry demands it. It's blue because the story demands it. And yet doing so creates misconceptions that viewers often carry into real-world conversations about chemistry, purity, and drug production. This chapter is dedicated to stripping away those misconceptions, not to criticize the show, but to reveal the fascinating truth underneath the fiction. Because in many ways, the real chemistry is more interesting, more complex, and more surprising than the Hollywood version. Why real meth doesn't turn blue, the chemistry behind color. To understand why real methamphetamine does not and cannot naturally turn blue, we need to examine the molecule itself. Methamphetamine hydrochloride is a salt, a simple combination of the methamphetamine base with a proton and a chloride ion. This structure is colorless because it absorbs very little visible light. Color in solids usually arises from conjugated systems molecules with alternating double bonds, complex ring structures, or metal ions that can absorb specific wavelengths. Methamphetamine has none of these. Its chemical structure is too simple, too transparent in the visible spectrum, too plain to produce a pigment. It does not contain the chromophores necessary to generate color. Without a chromophore, a substance appears white or colorless, because all visible light passes through or reflects evenly. In other words, meth is chemically incapable of being blue, violet, green, pink, or any other striking shade unless something else is present. An impurity, an additive, a contaminant, a dye. This is fundamental chemistry, not interpretation. The fictional blue hue in Breaking Bad is, from a scientific standpoint, an impossibility born from artistic liberty. Even if we imagine a scenario where methamphetamine accidentally absorbs impurities during synthesis, contaminated solvents, metal residues, side reactions, those impurities would create dull, inconsistent discoloration, not the vivid cerulean blue seen in the show. Real-life impurity discoloration is subtle, often faint, and almost always viewed as a sign of poor quality. Clandestine meth that appears tinted yellowish, pinkish, or brownish is regarded as the opposite of premium. This discoloration comes from incomplete reactions, unremoved solvents, or oxidized intermediates. The idea that an impurity could create a rich, uniform, gem-like blue is nearly impossible in clandestine conditions, especially when the final product is recrystallized in common solvents like isopropanol or methanol. These solvents would dilute and wash out any weak impurities long before crystallization occurred. For Walter White's meth to be naturally blue, an impurity would need to be both highly pigmented and chemically stable, enough to survive crystallization while not interfering with the meth synthesis itself, a contradiction to the process. The presence of such a substance would raise red flags for any chemist, because strong pigments often result from complex aromatic systems, which would drastically alter the chemical signature of the final product. In short, if meth were naturally blue due to an impurity, it wouldn't be high purity at all. This brings us to one of the show's most scientifically ironic choices, associating a strong color with purity instead of contamination. In the real world, drug enforcement agents seize meth that varies wildly in appearance depending on the methods and chemicals used. But purity is determined by analytical instruments, not eyes, not color, not shine. A batch that looks pristine might contain dozens of contaminants. A batch that looks cloudy might be comparatively clean. Even large, shiny crystals, another signature of Walt's product, do not guarantee high chemical purity. Crystal size depends on crystallization conditions, the rate of cooling, the availability of nucleation sites, the concentration of the solution, and the solvent used. A slow, controlled recrystallization can produce impressive shards even if the compound is impure. Conversely, rapid cooling, agitation, or high supersaturation can produce small, powdery crystals even when the substance is extremely pure. Crystal shape tells a story about crystallization conditions, not chemistry mastery. What about metal contamination? Could copper, cobalt, or another metal produce the blue coloration? Theoretically, yes, certain metal ions produce vivid colors when dissolved in solution. Copper-2 solutions are famously blue. But these ions would not bind themselves politely to methamphetamine without consequences. They would drastically alter the melting point, the solubility, the taste, the odor, the pharmacological effects, and the toxicology of the product. It would no longer be methamphetamine hydrochloride. It would be a contaminated mixture that could harm or kill users. The idea that a metal impurity could create a blue color, while still allowing 99% purity, is scientifically contradictory. A metal ion is not a negligible impurity. It is a major contaminant. You can't have a crystal infused with blue metal compounds and simultaneously call it 99.1% pure. The measurements simply don't add up. But perhaps the most forgotten scientific point is this: methamphetamine is almost always sold as a hydrochloride salt because the free base is unstable, oily, and difficult to crystallize. The hydrochloride form naturally forms white solids. This is why nearly all synthetic amphetamine-type stimulants from illicit labs to pharmaceutical production result in colorless crystalline products. Laboratory-grade methamphetamine made for research purposes is crystal clear or white. Pharmaceuticals designed to treat ADHD or other conditions are standardized in purity and color. Even high-purity amphetamine sulfate-related compound is white. There's simply no chemical pathway by which the pure molecule becomes bright blue on its own. So why did the show choose blue? The answer lies not in chemistry but in storytelling. Blue is symbolic. Blue stands out. Blue conveys purity in food marketing, luxury branding, and even cinematic color theory. It represents coldness, detachment, precision qualities, mirroring Walter White's transformation into Heisenberg. The writers needed a visual shorthand for excellence, intimidation, and legend. Something that instantly told the audience, this isn't just meth. This is the best meth ever made. The blue color functions as narrative iconography, like Superman's cape or Batman's cowl. It is not chemical truth. It is cinematic shorthand. This symbolic choice naturally created misconceptions in the real world. After the show aired, online forums and news outlets debated whether blue meth was real, whether it was stronger, whether it was hitting the streets. In a few isolated cases, dealers dyed their meth blue to mimic the show. Not because the chemistry demanded it, but because marketing did. The idea that color equaled power became part of the criminal mythology. But chemically speaking, dyed meth is often worse, not better, because the additives introduce unpredictable effects and impurities. The show inadvertently created a self-reinforcing cycle of misinformation. Fiction-inspired imitation. Imitation-inspired rumors. Rumors reinforced the myth, and the myth made the fictional version seem more realistic. But at its core, the idea is still false. Real purity is invisible. Real chemistry cannot be judged by color. And real methamphetamine, even at its highest quality, is always clear or white. To deepen the contrast between fiction and reality, consider how purity is actually measured. A forensic chemist evaluating methamphetamine doesn't look at it under a lamp or judge the color. They use gas chromatography combined with mass spectrometry. They examine retention times, fragmentation patterns, ion signatures. They calculate purity by quantifying peaks on a chromatogram, scientific measurements that have nothing to do with appearance. A sample that looks beautiful may test at 40% purity. A sample that looks dull may test at 95%. Chemistry cares about molecules, not aesthetics. This truth dismantles the entire visual mythology built around Walter White's signature product. And yet the blue crystal myth persists because it is compelling. And perhaps this is the greater point. Sometimes, what makes a story unforgettable is not the accuracy of the science, but the emotional power of the illusion. Blue meth became a symbol for Walter's descent, his brilliance, his vanity, and his ruthlessness. But here, in this documentary, our job is not to celebrate the fiction, it is to reveal the truth beneath it. And the truth is this: no matter how iconic the image, no matter how memorable the color, real chemistry never behaves that way. Reality is less flashy, but far more fascinating. The illusion of crystal perfection, how shape, size, and shine mislead us. When audiences see Walter White's meth, they aren't just seeing a fictional drug. They're seeing a crafted illusion, an object designed to evoke purity, brilliance, and superiority. The massive, glass-like slabs glinting under harsh lights signal one thing: mastery, power, perfection. But crystal perfection is one of the most misunderstood components in chemistry, because the human eye isn't built to recognize the truth behind a crystal's shape. What looks beautiful can be contaminated. What looks dull can be flawless. Nature produces large crystals and small crystals based on conditions, not on chemical virtue. In reality, crystal size is nothing more than the story of how a substance cooled, dissolved, or precipitated. Yet television uses crystal aesthetics as shorthand for purity, reinforcing a misconception so widespread that even experienced viewers begin to trust their eyes over the actual science. Crystallization is governed by kinetics and thermodynamics, two forces constantly tugging at each other. If a solution cools slowly, allowing molecules time to align into orderly lattice, the resulting crystal will be large, smooth, and impressive. If the solution cools rapidly, molecules don't have time to settle properly. The result is a smaller, irregular, cloudy crystal. Neither scenario inherently reflects the amount of impurities present. You could take an impure substance, dissolve it, cool it slowly, and produce large crystals full of imperfections at the microscopic level. You could also take an extremely pure substance, crystallize it quickly, and end up with tiny grains that look unremarkable. This is why real chemists don't judge purity by appearance. Yet the show wisely cinematically turns crystal aesthetics into a signature of scientific excellence. Even in legitimate labs, perfect large crystals are surprisingly rare. They require precise control over temperature gradients, solvent purity, humidity, and supersaturation levels. Walter White producing enormous slabs of meth in an RV or a makeshift industrial lab might look impressive. But scientifically it raises questions. Where are the controlled cooling baths, the temperature feedback systems, the slow evaporation chambers? Where is the stabilization equipment needed to ensure that the solution cools at exactly the right rate to produce crystals the size of window panes? Large crystals demand patience and environmental consistency, two things almost impossible in improvised clandestine conditions. And yet in the show they appear regularly as though conjured from thin air, their perfection symbolizing Walter's precision. It's a beautiful cinematic device, but scientifically implausible. Then there is the shine, the glassy, reflective sheen that makes Walter White's product instantly recognizable. Shine is another aesthetic that television uses to communicate purity. But, in reality, shine has far more to do with the physical structure of a crystal surface than with its chemical quality. A crystal with smooth, well-formed facets will reflect light efficiently. A crystal with chipped edges or rapid growth defects will scatter light and appear dull. But both crystals may have the same level of chemical purity. The show exaggerates the reflective properties for dramatic effect, making the meth sparkle like diamond fragments. Real methamphetamine crystals are typically translucent and less theatrical in appearance. They have irregular shapes, jagged edges, and are often coated in microscopic imperfections. Under a lab light, they look more like crushed salt than gemstones. Another aspect often overlooked is moisture content. Real meth, especially poorly dried meth, can appear cloudy or sticky due to residual solvents. These solvents can reduce crystal clarity, affect how the drug burns or vaporizes, and introduce additional toxicity. Walter's meth, by contrast, looks bone dry, fracture perfect, and completely uniform, qualities that would require sophisticated drying techniques like vacuum ovens, desiccators, or carefully controlled furnace environments. Even legitimate pharmaceutical labs struggle with moisture retention in crystalline products. Yet the show presents flawless dryness as an effortless result of Walter's genius. Once again, the science bends to the storytelling and the illusion becomes part of the myth. There's also a deeper misconception here, the assumption that crystal perfection automatically means better. In chemistry, perfection is an aesthetic trait, not a chemical one. Many substances crystallize beautifully despite impurities locked inside their structures. A crystal is merely a repeating arrangement. Impurities can be trapped between layers, incorporated into the lattice, or hidden in microscopic domains invisible to the naked eye. This is why forensic labs grind samples into powder before testing them, because appearance does not guarantee purity. Grinding ensures that the sample analyzed is uniform. Without grinding, one could test a piece of crystal that is more or less pure than the rest. Yet in Breaking Bad, the product appears uniformly superior in both appearance and chemical quality, an impossibility without rigorous lab analysis after each batch. Complicating things further is the role that solvents play in the final aesthetic. The choice of solvent dramatically impacts crystal quality. Common solvents used in clandestine meth production like acetone, isopropanol, or ether aren't pure enough to create flawless crystals. They're not distilled in clean rooms. They often contain water, stabilizers, or industrial-grade impurities. These contaminants interfere with crystal formation, leading to cloudy or misshapen structures. Yet the meth in Breaking Bad has none of these blemishes. Despite being produced in environments that would introduce them at every stage. Again, the show isn't interested in solvent behavior. It's interested in visual storytelling. The crystals gleam because the narrative requires them to gleam. But perhaps the most misleading element isn't the crystal size or the shine, it's the consistency. Every batch of Walter's meth looks identical. In real chemistry, this level of consistency is incredibly hard to achieve without automated processes, high-precision equipment, and rigorous quality control. Even pharmaceutical companies using the same recipe under the same conditions encounter batch variation, slight temperature fluctuations, slight changes in solvent purity. Even slight differences in stirring speed can alter crystal morphology. Yet Walter, working with improvised equipment, produces products so visually consistent that it resembles a mass-manufactured commodity. This gives the illusion that chemistry behaves predictably when performed by an expert. In reality, chemistry is sensitive, temperamental, and often non-intuitive. Expertise helps, but it does not override the physical world. And certainly not to the degree depicted in the show. The psychology behind perfect crystals is also worth exploring. Humans equate visual order with quality. We trust symmetry. We trust sparkle. Something that looks sharp and pristine must be superior, even if we don't understand why. This bias influences real-world drug users and dealers, just as it influences viewers watching the show. The myth of crystal perfection becomes self-reinforcing. People believe purity looks a certain way, so dealers try to make their product look that way, even when the appearance has nothing to do with the chemistry. In this way, Breaking Bad didn't just fictionalize crystal meth, it shaped cultural expectations around it, blending science and emotion into a single, iconic image. But here lies the deeper truth. Real crystals don't care about myth. Real chemistry doesn't align itself with the visual metaphors that storytellers prefer. The blue color, the perfect slabs, the sparkling surfaces. These elements create a compelling narrative arc, but they distort the public's understanding of how crystalline substances actually behave. And so the gap grows between perception and reality, between what chemistry truly is and what it is allowed to represent in fiction. And it's that widening gap we're here to close, line by line, truth by truth, myth by myth. When purity becomes a myth, why real chemistry has no blue? Think back to the moment when Breaking Bad truly stamped its identity on pop culture. It wasn't just the desert shots, the RV, the gas mask, or the infamous Heisenberg hat. It was the color. The unmistakable, crystalline blue that became synonymous with Walter White's mythical product. It looked otherworldly, almost supernatural, as if its maker had transcended the boundaries of chemistry. But color is never just color. In science, color is a signature and emission of what's present, what's missing, and what the molecules themselves are whispering in their silent, structured language. So when we ask what blue meth means, we're really asking what impurities are responsible. Because pure crystals, especially the kind the show claims, don't glow with dramatic flair. They don't shimmer neon. They don't announce themselves. In the real world, purity is boring. It's colorless. It's quiet. It's unexciting. And that's because molecules, when arranged in their most ideal states, absorb and reflect light in predictable ways. The moment you add color, you're adding chemistry. You're adding flaws. You're adding something that doesn't belong. Let's break that down. A crystal becomes colored for a few reasons: transition metal contamination, organic dye residues, oxidation byproducts, or incomplete purification. Those are the most common culprits. None of them are signs of superior craftsmanship. They're signs this batch didn't finish the race. They're the molecular equivalent of a typo in a story, a smudge on a painting, a wrinkle in a pressed suit. So if Walter White's product were genuinely 99.1% pure, as the show repeatedly claims, the question becomes, what is that 0.9% doing? How is it so potent that it can overpower the optical clarity of the entire rest of the molecular structure? And more importantly, why does its color remain consistent across thousands of batches? Consistency and impurity is not the hallmark of precision. It's the hallmark of error. To produce the same error repeatedly with machine-like perfection is ironically more difficult than producing a truly pure, clear crystal. Let's go deeper into the science. Methamphetamine hydrochloride, when synthesized correctly and crystallized efficiently, forms clear shards resembling broken glass or ice. The reasons are simple. The molecule is small, structured, and lacks chromophores, chemical groups that absorb visible light. Without chromophores, the crystal has nothing to tint it. It remains transparent. When coloration appears in real labs, and yes, forensic records show countless tinted batches, it usually comes from unreacted precursors or side products. A common impurity that creates yellow or brown tones comes from phenylacetone oxidation. Pink or red batches often come from dyes and cutting agents. Blue specifically most often comes from copper contamination pipes, coils, or drying surfaces where tiny traces of the metal leach into the product. But copper contamination would not only tint the crystal, it would be toxic, especially in large-scale distribution. Yet the show portrays the blue color not only as safe, but as the badge of superiority. This is where the narrative begins to drift so far from reality that even a forgiving chemist would raise an eyebrow. Chemistry doesn't reward creativity when it comes to impurities. It punishes it. Consistency comes from control, sterility, precision, and well-calibrated equipment, not from the chaos of clandestine manufacturing. Which brings us to an uncomfortable truth the show glosses over. Any illicit operation producing batches at the purity level, Walt claims, would not be using jerry-rigged home setups, dusty basements, damp underground tunnels, or RV cookers. They would require pharmaceutical-grade reactors, controlled humidity, inert atmospheres, drying vacuums, and meticulously maintained piping. Yet even pharmaceutical facilities don't produce blue crystals unless something goes wrong. But what about the show's in-universe explanation? Writers and fans often say, the blue is just a fictional cue so the audience can distinguish Walt's product from everyone else's. And that's correct. It's a visual storytelling device, a signature, a metaphor for Walter's transformation. But the moment the show tries to justify the blue color with claims of higher purity, this is where science gently taps the writers on the shoulder and says, actually, that's not how any of this works. Because if purity is the bragging point, then the crystal should be clearer, not more colorful. If the product is uniquely powerful, the explanation should lie in pharmacology, not aesthetics. And if the chemistry is perfect, the results should be invisible, not iconic. Now, let's take a moment to address a misconception viewers often share. The belief that the blue, meth's superiority comes from the blue. In reality, visual indicators are never used to evaluate potency. They are unreliable, inconsistent, and purely surface level. Forensic testing focuses on chemical signatures, mass spectrometry peaks, GC-MS profiles, reagent test reactions, melting points, and optical purity. None of these metrics rely on color. At no point does a forensic chemist look at a blue shard and say, "This must be premium." In fact, a trained analyst would immediately suspect adulteration. In science, unusual visual features don't suggest brilliance, they suggest failure. There's also another layer of scientific irony here. The more crystalline and perfect a substance appears, the less likely it is to be pure. Large, beautiful crystals form slowly. They require time, temperature, stability, and space to grow, conditions that often allow impurities to settle into the lattice. Smaller, powder-like crystals form under fast precipitation conditions and can actually be more pure. So Walt's large blue crystals aren't just scientifically suspicious, they're chemically backwards. A lab chasing purity wouldn't proudly display large decorative shards. They would aim for consistency, homogeneity, and reproducibility, not dramatic visual appeal. And here's the twist. Even though the blue color is fictional, the idea of a signature in purity is very real in forensic chemistry. A unique contaminant can be used to trace a batch back to a specific manufacturer. In real cases, these impurities have helped authorities identify production methods, equipment types, even the age of a particular synthesis pathway. Walt's product, with such a consistent and dramatic coloration, would be among the easiest illicit substances in history to trace. Every law enforcement database in the country would flag it instantly. Every agent would know exactly where it came from. Every chemist would recognize the signature. The show depicts it as elusive, but scientifically, it would be the most identifiable contraband ever produced. So what does all of this mean? It means that the mythos of blue meth taps into a deeper instinct, our attraction to the idea that genius leaves a mark. That brilliance makes itself visible. That a chemical mind like Walter White's would produce something different, not just chemically but aesthetically. But real chemistry hides its genius. The cleaner the reaction, the quieter the result. The more perfect the purification, the more invisible the product. Purity doesn't glow with color. It disappears into clarity. In reality, the only way Walter White's iconic blue crystal could exist consistently is if it were intentionally dyed. And ironically, that would make it less pure, not more. A fraudulent marketing trick, not the pinnacle of chemistry. A contradiction in the very identity Heisenberg built. Yet perhaps that's the hidden poetry of it all. Because while Heisenberg wanted to be remembered as a master chemist, what truly made him powerful wasn't purity. It was perception. Not science but myth. Not chemical truth but psychological impact. The blue wasn't a property of the meth, it was a property of the legend. And sometimes in storytelling, legends need their own spectrum of light. Even if chemistry would argue otherwise. The purity paradox, why 99.1% is both too high and not high enough. When a TV show tosses out a number like 99.1% pure, it sounds scientific, precise, impressive, almost mythological. Walter White's entire reputation is anchored to that figure, a numerical crown he wears as proof of genius. But in real chemistry, numbers like this are not symbols of brilliance. They are the result of instruments, methodology, and consistent process control. So when the show declares that Walt's product is 99.1% pure, it's making a claim that is far more complicated than it appears. Because in a real forensic lab, purity isn't determined by dramatic pronouncements or the visual impressiveness of crystals. It comes from analytical chemistry, an unforgiving discipline that does not bend for narrative clarity. Let's begin with how purity is actually measured. No chemist examines a crystal, notes its shine, and concludes perfection. Instead, they use gas chromatography, mass spectrometry, infrared spectroscopy, melting point determination, and chemical reagent analysis to quantify exactly how much of a substance is the intended molecule and how much is everything else. These processes differentiate between the target compound, intermediates, leftover reagents, structural isomers, chiral impurities, and trace contaminants. A purity of 99.1% means that 0.9% of the material is not methamphetamine hydrochloride. But in the world of drug chemistry, that 0.9% can be thousands of molecules. It can be metals, solvents, polymers, stabilizers, catalysts, side products, decomposition compounds, or something as mundane as dust. And every one of these contaminants has fingerprints, something that leaves a reliable color signature like copper. Cobalt, chromium, or organic dyes would not go unnoticed in analysis. It would show up immediately. The lab tech reading the chromatogram would simply circle the unexpected anomaly and say, "Something's off." This raises an interesting contradiction. The show's claim of near-perfect purity doesn't align with the dramatic visuals they use to support it. If Walt's meth were truly 99% pure, it would appear clear and colorless. If it appeared dramatically blue, the purity would instantly be lower. You cannot have both. Purity and coloration are natural enemies. One defeats the other. And yet, the legend of Heisenberg depends on pretending they can coexist harmoniously. This forces the viewer into a subtle suspension of scientific disbelief, one so seamless that most people never even think to question it. But let's imagine for a moment that a real chemist tried to produce methamphetamine at this exact purity level. How would they do it? They would require reagent-grade materials, verified precursors, vacuum-distilled intermediates, chemically resistant apparatus, inert gas blankets, precise heating mantles, digital temperature monitoring, rotovapes for solvent removal, column chromatography for purification, recrystallization cycles, and analytical verification at each step. They would need a clean room-like environment, not an RV with dust in the air and insects on the countertops. They would need filtration systems free of contaminants, controlled humidity, and storage conditions that prevent solvent absorption or decomposition. They would not be working in basements with rusty pipes, or underground bunkers with poor airflow, or makeshift labs where a spilled solvent becomes a life-threatening hazard. And perhaps the largest contradiction of all, even pharmaceutical companies rarely achieve 99.1% purity without intensive process optimization. Yet Walt is shown hitting this number on his very first large-scale attempt, under crisis conditions, with improvised equipment. Not impossible, but highly unlikely. It takes chemists years of experience to refine a reaction pathway. It takes entire teams to optimize production. Walt is one man working in chaos. And while the show portrays him as a once-in-a-generation chemistry mind, truly elite chemists know that consistent purity requires something far beyond intelligence, stability, patience, structure, a controlled environment. The very things Walt never fully has. Then there's the issue of batch consistency. In the series, Walt's meth is repeatedly described as flawless. Every shipment is identical. Every crystal matches perfectly. But real-world chemistry doesn't work that way. Even highly controlled pharmaceutical production has variance between batches. Slight variations in moisture content, solvent evaporation rates, catalyst freshness, or crystal growth conditions can cause subtle differences. Walt's ability to produce identically flawless crystals under wildly different conditions, RV? House, super lab, mobile lab borders on the miraculous? It would require not just mastery, but omniscience, as if the chemicals themselves are bending to his will. And while that makes great television, it is not how molecules behave. They don't care about personal brilliance. They care about physics. They care about energy. They care about structure. They care about equilibrium. And here's where we stumble into one of the series' most unintentionally ironic truths. Walt's meth is only perfect because the show needs it to be. It's a narrative device, a symbol of transformation, a physical representation of his identity fracturing into Heisenberg, cold, precise, and ruthlessly consistent. But real purity is fickle, difficult, hard-fought. Even small-scale research labs struggle to maintain it across experiments, and Walt's operation, with its makeshift facilities and constant disruptions, would face enormous challenges. Dust alone would be a perpetual enemy. A single speck can ruin an entire recrystallization cycle. A minor fluctuation in temperature can alter the saturation point. A miscalibration in equipment can introduce trace impurities that would immediately show up in a forensic analysis. Then we arrive at another fascinating paradox. 99.1% isn't even the pinnacle. Truly, pharmaceutical-grade substances can reach 99.8%, 99.9%, even 99.95% purity with proper resources. But at that point, the margin for error becomes razor thin. Achieving these numbers is not an artistic endeavor, it's industrial. It requires automation, optimization, and technology. Elemental analysis would detect 0.1% impurities. High-performance liquid chromatography would reveal trace anomalies invisible to the naked eye. And yet Walt's purity number remains static throughout the series, as if frozen in narrative amber, not improving despite his growing resources, not fluctuating despite environmental changes, not reflecting the reality of complex synthesis. This static purity number is actually a sign that the show's writers picked a value that sounded scientific but not unbelievable to a casual viewer. High enough to imply mastery, but not so high that it feels godlike. But a real chemist would ask questions. Why 99.1%? Why not 98.7%? Why not 99.8%? Why not fluctuations between batches? Purity is not fixed. It is dynamic. It responds to environment, equipment, precursors, atmospheric conditions, and the skill of the person conducting the work. The show treats purity as a personality trait, but science treats it as a measurement. And measurements have no loyalty to narrative arcs. Yet even with all these contradictions, there's something compelling about how the show uses purity as a symbol. It transforms chemistry, a discipline of uncertainty, into something mythic and absolute. Walt's purity number becomes a stand-in for identity, a metric for pride, a weapon of intimidation, a representation of his inner dissent. It's no longer a chemical property, it's a psychological one. And in that sense, the 99.1% purity claim serves a purpose far beyond technical accuracy. It becomes a mirror reflecting who Walter White believes himself to be: exceptional, flawless, beyond reproach. But the irony and the tragedy is that chemistry itself would never grant him that perfection. Only storytelling could. If you got this far, take a moment to subscribe and share. The myth of the master chemist, why Walt's process would fall apart in reality. There's a moment in Breaking Bad when Hank Schrader, looking at a bag of blue crystals under bright fluorescent lights, mutters that whoever made this product isn't just a cook, he's a chemist. And it's a powerful line. It frames Walter White not as a criminal, but as a scientist operating in a world beneath his potential. But the moment you analyze his process through the lens of real chemistry, a different picture emerges, one where the mythology of Walt's brilliance clashes with the realities of chemical synthesis and laboratory discipline. Because chemistry is not just about reactions. It's about conditions, control, cleanliness, consistency. And those are the areas where the show's portrayal falters most dramatically. Let's start with one of the biggest issues: environmental contamination. Real labs are designed to prevent it with relentless thoroughness. Air filtration systems, laminar flow hoods, particle-controlled environments, sterile equipment storage, temperature-stable rooms, surfaces engineered to resist chemical absorption, floors that don't shed dust. Even chemists themselves become potential sources of contamination. Hair, skin, clothing, fibers, exhaled moisture, everything must be accounted for. But Walt's labs violate these rules on a molecular level. The RV has open windows, desert dust, rust, condensation, insects, and chemical residues from previous cooks. The basement lab has humidity, domestic bacteria, carpet fibers overhead, and structural dust. The underground super lab, while visually impressive, has people constantly walking in, coughing, sweating, handling tools, leaving fingerprints, dropping debris, and introducing biological contaminants. Every one of those elements can interfere with crystallization, purity, and reproducibility. Real illicit chemists, far from being careless criminals, often fail, not due to incompetence, but because their environment is simply not suited for advanced synthetic work. Walt, by contrast, produces flawless crystals in places where a real chemist would struggle to produce a stable intermediate. It's not impossible, it's just deeply unrealistic. Next, consider the issue of solvents. Real labs must remove solvent residues with precision because even small traces can radically alter purity. Methanol, isopropanol, ether, toluene, acetone. Each requires different evaporation methods, drying techniques, and pressure controls. Walt's use of heat guns, open-air evaporation, and uncontrolled airflow would leave volatile residues deeply embedded in the crystal lattice. These residues not only reduce purity but change the crystal's appearance, smell, melting point, and density. Forensic labs routinely detect these contaminants. That's why real confiscated meth often smells like solvent, because the evaporation process wasn't controlled. Yet in the show, Walt repeatedly uses improvised setups, boiling solvents on bare hot plates, evaporating them in open rooms, and performing recrystallizations without vacuum systems, while still achieving absolute purity. That's not chemical genius. It is narrative magic. Now look at reaction kinetics. Every chemical reaction has ideal temperature ranges, mixing speeds, diffusion rates, and catalyst conditions. Deviate even slightly, and side products form sometimes invisibly, sometimes dramatically. Real chemists must adjust settings minute by minute. Walt, however, often cooks under stress, distraction, time pressure, or improvised conditions. He performs delicate reactions while arguing, while fighting, while fleeing, while working with untrained assistants, while dealing with emotional collapse. In a real lab, those distractions would cause measurable errors. Even a few minutes of overheating could degrade the product. Even a moment of undermixing could cause incomplete reduction. Even a small temperature fluctuation could shift the reaction path entirely. But Walt's reactions always work, always proceed to completion, always produce the same purity. The idea that chemistry would reward this chaos with perfect results is one of the show's most entertaining illusions. Then there's the issue of batch scaling. Scaling a reaction from a beaker to a drum is not simple multiplication. It changes the heat profile, the reaction timing, the surface to volume ratio, the solvent penetration, and the rate of intermediate formation. Many reactions that behave beautifully at small scale become unstable, violent, or non-productive at large scale. Professionals spend months optimizing scale-up procedures. Walt never does. He jumps from small runs to industrial quantities without troubleshooting, without adjusting equipment design, without studying the entropy flow, without using thermal jackets or insulated vessels. In reality, he would lose control of temperature, generating runaway reactions or incomplete conversions. Yet in the show, batch size has no effect. The chemistry is portrayed as frictionless. Another overlooked factor is chiral purity, the balance of right and left-handed molecular forms. Methamphetamine has two enantiomers, one active, one mostly inactive. Achieving a high ratio of the active form requires specific catalysts and careful reaction conditions. Real illicit meth often contains racemic mixtures. Walt's supposed 99% purity suggests he not only synthesizes the molecule correctly, but achieves near-perfect enantiomeric selection. That alone would make him a historic figure in organic synthesis. But the show never acknowledges this complexity. They use purity as a label, not as a scientific outcome. Perhaps the most scientifically unrealistic aspect of all, Walt's product never shows degradation over time. Real crystals absorb moisture. They oxidize. They change texture. They lose structural integrity. Even highly stable drugs require proper storage to maintain quality. But Walt's meth is always pristine, as if frozen in stasis. Whether it's been in storage for hours or months, transported across borders, handled by dozens of people, or exposed to humidity, the crystals never cloud, never soften, never reform, never dissolve at the edges. They remain perfect because they are props, not chemicals. And yet, despite all the scientific inaccuracies, there's something deeply compelling in how the show elevates chemistry to a form of identity. Walt's mastery isn't just technical, it's emotional. His product symbolizes his self-worth, his ego, his bitterness, his transformation into someone who finally feels seen. That's why the show exaggerates the science, because the meth isn't just meth. It's a narrative device representing power, control, and the illusion of perfection. Real chemistry doesn't grant that perfection. It resists it. It demands precision, concentration, patience, humility. Walt's process lacks all of these traits, and yet his product is divine. That contradiction is where the storytelling thrives. It's not about accuracy, it's about mythology. Walt isn't a chemist in the scientific sense, he's a chemist in the mythic sense, a sorcerer crafting a substance that transcends reality. And legend, unlike chemistry, does not require consistency. It requires symbolism. In the end, the greatest scientific fiction in Breaking Bad isn't the blue color or the purity or the flawless crystals. It's the idea that chemistry will bend to a man's emotions, his determination, his ego, or his narrative arc. Real chemistry is indifferent. It obeys natural laws, not dramatic ones. But in the world of Walter White, chemistry becomes a mirror reflecting everything he wishes he were: perfect, powerful, untouchable, exceptional. A purity myth wrapped in blue glass. A story, not a science.